Okay, there we go. See, I can shout as loudly with a microphone as without a microphone. Wonderful. Ah, beautiful. For everyone who's watching the videos later on, this talk is going to be in English, but... Привет, Екатеринбург! Как дела? Все хорошо? Да? Очень хорошо. Отлично. Давайте. The rest of the talk is going to be in English, though. So, who am I? I'm Martin Splitt. I am from Zurich, Switzerland. Wonderful country. The flag is a big plus. And I am a very, very professional person. This is my LinkedIn photo. I highly recommend doing things like this for your LinkedIn profile because it keeps away recruiters for some reason. But nonetheless, I am the head of engineering at Archeologic, which is a small company that does things that helps you build web applications that are in 3D and allow WebVR things. And we work a lot and support a lot the Blender community and the A-Frame community, so definitely check it out. You'll see a link in a short moment. I'm also a Google developer expert for web technologies and Polymer. So if anyone here using Polymer? I have a friend here. You all, do whatever. This person is who cares. So anyway, I'm also working with the Mozilla community a lot, and I am working with the W3C standards community, and I would like to encourage all of you, go to the W3C GitHub organization, find the specification that you have a problem with, and open an issue or make a pull request. Because web standards happen together with the community, and we need more of your input as developers to make the web better. And I work at this thing that's called 3D.io, which is the Archeologic product that allows you to do like 3D stuff in the web. Anyway, today I'm not going to talk about WebVR or 3D. Today I'm going to talk about rendering performance. And I think we should start by what we've got, which is HTML, CSS, and JavaScript, to what will be produced when it's going on screen, the actual rendering part, which is pixels and all that kind of stuff. And then we're going to have a look at how that looks when we build web applications in the real world. And then there's going to be a quiz, because everyone loves to be asked questions, right? And don't worry, it's not like I'm not going to take grades or something. Like, it's not that not back to school kind of thing. And then if we have time, we're going to look at WebGL and Canvas 2D as a kind of like bonus round, as a reward for the quiz, if you all do good on the quiz. Anyway, let's start with trees, because I like trees. There's two particular trees that we have been hearing about maybe already somewhere else and also today. And there's a third one that we just heard about, which is the accessibility tree, but that's not that much about rendering, so I left that one out. So let's have a look. So when we write web applications, we write things like this, hopefully. If you're writing something else, like an empty thing and then just JavaScript runs, I have the first performance improvement for you. Don't do that. And if we have semantic markup like this, then what happens is the browser basically starts parsing it as it comes in. So once the file starts downloading from the internet, the browser goes, ooh, this is probably HTML. Oh, look, yeah, it is HTML. That's convenient. So I have a document. And in the document, I have a body, which is good because a document without a body is a bit blank. And then I have this headline here that has some text in it. And then there's this image as well. And voila, we have our DOM tree. At the same time, there's another tree being built. I'm not showing that one, which is basically parsing the CSS information as it comes in to figure out how these things are going to be styled later on. So basically, when we say parsing, what we have is a streaming parser that does something that we can't do yet with fetch or XML HTTP request, which is as the data comes in, we are parsing it already. If you do AJAX, you're usually just waiting until everything has arrived and then you can parse it, which is a bit shit, but that's what we have the Streams API coming up for. Look for the Streams API because it's going to be awesome, because it gives us access to things like this. So these two parsers actually create a tree structure. Okay, cool, and it's the DOM structure for the document contents, and it's the CSSOM for the document styles. All right, so that means we still haven't got the website yet, right? Because the only thing we know at this point is this tree. And what does this tree mean? Well, we know what we've got, but we have no idea how it's going to look exactly on the screen and where it's going to go and how much space it's going to take, and none of this is known to us at this point. That's where layout comes in. And layout, the first thing it does is it looks at the CSSOM and the DOM, and goes, all right, so this thing is this big, and it can do this, for instance, by using things like the font size and width and height properties. So if I have a box that's 200 by 200, then sure, that's going to be 200 by 200 pixels. Great. If I have the text hello world in 20 point, then I have to do some calculations, and then actually I know how large this box is going to be. And once it figures out how large the box is going to be, it looks at the window, because it has to figure out how much space it has available, because we then have to figure out how we position things, right? So if a text is too long for one line, we have to break it over, and that means it changes the size of the box. And so on and so forth. If we resize the window, we have to do this again, because then the space is different, so we have to move things around again. If we zoom in and out, if we scroll, all that kind of stuff might cause, now scroll not, but like all the other things, if we move around the size of the window, it might move around things, and then we have to do layouting again. And it does that based on these trees. Okay, so we have the thing that it needs, which is the trees. Now we can figure out other things. And it looks like this. So here, as the data comes in and as the tree is being built, it's layouting and it's figuring out how large each of these items will be and where they go on the screen, and it figures it out quite well. And basically, if I now resize the window, it has to do this again, because things might move around, or maybe not, it depends. So now we know these boxes. We know where stuff goes and how large it is, but that's still not how our website looks like when we open it in the browser. And if it does, then I'm very sorry. You should probably reinstall your browser, because that's not how the web's supposed to be looking like. So at this point, we have to start painting. God, I hated Artscraft in school. Oh God, I'm so bad at painting. I'm really happy that the browser does this for us. But if you've ever done painting, you know that it's a good amount of work, even though Bob Ross makes it look like super easy. And I'm always like, no, don't do it, Bob Ross. And then oh, this looks cool. And the browser's kind of like that, the pixels things in and goes like, happy little accidents, and then it looks amazing, and you have a beautiful website. And what goes into that is I mean, okay, it's painting, but what does that mean? I can understand what it means to paint on a canvas with physical things, but what does it mean to paint on a screen? To explain that really quickly, I gave you a 3x3 screen, which is probably a phone from, I don't know, 10 years ago or something, and this is what the screen looks like to the computer. It's a bunch of numbers. And that's because each of these pixels is actually 3 tiny little lights, a red one, a green one, and a blue one. You might have heard RGB. That's what they are standing for. And I know this is kind of basic. Don't worry. We are ramping up to something here. And depending on how bright each of these dots are, the pixel has a different color. So we have a bunch of numbers here. Great. Now, obviously, the table that we are seeing here is not really what the computer is seeing, because the computer doesn't give a shit about the table layout. What the computer cares about is the values at the right positions. So we can just as well represent this as an array. So when we're talking about screens or pixels, what we mean is an array of numbers. Who here knows how arrays work? That's pretty good. First quiz question answered, and everyone else is like, what? Who am I? What year is this? That's okay as well. So the screen is an array, and each of these arrays is actually 4 numbers, because there's transparency as well. Now, we can't make this screen transparent, right? It's not a holographic thing or something. It's not turning into glass at some point. So how does that work? Well, we assume that we have a base color, which is white or black or green or blue or whatever, and then we kind of use the other 3 numbers and combine them and multiply them with this 4th value to actually figure out how much these values influence the screen. So it's not going to turn transparent. Don't worry about that one. So basically, when we render, we are changing numbers in an array. That doesn't sound hard. I mean, I've done that. I've done that quite a while ago, and I've done it again. And so far, I have not failed doing that. So pretty good. We have a bit of a chance of getting this done, right? Rendering is not as hard as it seems. So yay, we can now start painting. Happy little accidents. So when we paint, we usually work with rectangular things. If you have opened an image file, you might have noticed they are usually rectangular. And that's okay, because we have this transparency value, so that means we can say, this pixel here, ignore it with the rest of the screen. That's fine. And these images, these rectangles, are usually either called images, textures, or layers, depending a bit on who you ask. If you're talking to 3D people or game developers in particular, they are going to call these images textures, or sometimes sprites if it's 2D old school developers. And if you talk to browser people and CSS people, they are probably calling them layers, but it's the same thing. So we have different terminology. I might mix up the terminology every now and then, but it means the same thing. It's images. It's a rectangular array of numbers. Okay, we can do that. And then there's a step that I haven't talked about, which is compositing. And this is cool. This is good stuff, because, okay, now we have a bunch of these rectangles, and then we have the screen, and we have to kind of like, compositing is the process of going, I'll put this here, and this one here, and then this one in the middle. So that basically, we have the possibility to just really quickly copy things onto a screen, and that's called compositing. Why is that a useful thing? Why is that a nice thing? Well, imagine that we have these two images and 2 pixels from 2 different images. We have a red one, and we have a green one. Now, the green one here is this 4th number here is the alpha value. That's the transparency that we've been talking about beforehand. It's half transparent, and this is 3/4 transparent. So if this value would be 255, that would mean just use that thing and ignore everything else. But these values are not 255. So basically what we have to figure out is, how do we make the screen go red, green, and blue? Because the screen, again, can't take transparency, really. So what we're doing is we're multiplying these two with the transparency values and then mixing them by adding them. And then we get a color that looks like it is actually half transparent. So basically, these colors are slightly transparent, so it has to be a slightly darker color than it was before. Okay, and this can be used for other things. For instance, animations. So instead of having to paint all the pixels all over again, just imagine that, having to literally, that's what people in cartoon studios are doing, right? They are painting everything again and again for each of the frames. That's why it takes ages to make these things, or 500 Korean people somewhere doing that all over the time. Now, in our computer, we don't have enough space, especially not on phones, for 500 Korean people. And I say Korean people because they're freaking amazing, like, artists. That's all. Could be Russian people as well. I guess there's a bunch of really good Russian artists as well. I've met a few in St. Petersburg. Awesome work. Anyway, I don't have place enough in my phone to have 500 Russians there, right? So instead, what I'm doing is I take these rectangles and composite them, and do that all over again, hopefully 60 times a second. So that can look like this. So I have my background, and then I put my Nyan cat here. And I put that on the screen. And then, really quickly afterwards, I do the same thing. I just copy this rectangle on a different position, and then I do it again, and I do it again, and then I end up with my clicker not working. This. And so on and so forth. So that's kind of how animations really work. It's just compositing them a lot of times, because the computer is not fast enough to paint all the pixels all the time, because it's a lot of work to actually do that. Okay, but how exactly do these combinations work? Like, what do we actually do? Do we kind of like copy it over and then add the numbers, as we did in one of the slides earlier? Or how do these two things go together? And it turns out that we have a thing called a shader. So we have a bunch of images. We use them as inputs for a shader, which is a program that runs on the graphic card or on the graphics chip, which is called a GPU, and it produces one color value that then goes onto the screen. What the hell is a shader? Like, okay, it's a function, it's a program that runs on the GPU. What? Okay, don't worry, I've got you covered. So here we have the CPU and the GPU. And there's one interesting difference. The GPU has a lot of small brains. The CPU has a few larger brains. So, I mean, that's like an extreme case where we only have one core. Normally you have like 4 or 8 cores, depending on what kind of phone you've got and computer you've got. But for the sake of simplicity, let's say we have one CPU, but we have in one GPU, we have a lot of smaller like brains that actually execute things. So why would you even want a CPU? I mean, obviously, I want the thing that has more brains, like a zombie, brains, right? So, but there's a difference in between these brains, or these calculators, if you want to really go for them. So the CPU actually is really clever when it has to do things like this. It has to read from a piece of memory, and it has to write from a piece of memory, and then there's like branches, and there's loops, so basically it has to do like the same kind of thing all over again, depending on what data there is. And it's like, okay, so if there's this value here, then I put that value over there. But if it's not, then I put another value there. So this kind of thing, CPUs are really good at because they are like predicting the future and stuff. It's really, really crazy stuff. And it's amazing as well. But that's what they are really good at. And then the GPU goes, boy, that is... I do not have an answer to your question, but I have a lot of respect for it. Bye! And that's the situation. So obviously we're now like, these things can't do jack shit, so I just go for this one, right? Well, not quite, because there turns out to be a kind of math problem that is really good if you have a lot of like not so clever cores thinking about them. So for instance, here we have a bunch of matrices that we want to multiply. And that works by basically saying, take this, and put it here. There's no dependencies. You see, it's not like, and if it's this that says 5, then, no, it's just like, take this, and here. And it does that all over again. So the CPU would do that all over again, one by one. But here, these little brains go, ooh, we know how to do that. So we do it all in one go. Awesome. So that's much faster. But it can't do the problems, or can't work with the problems that the CPU can work with. But okay, so we can do matrix multiplication, or what's called SIMD, which is like single instruction, multiple data, because the instruction is the same, it's just a lot of data that we have there. But how does that help us with rendering, right? Well, if we think about it, these tables here, and here, and here, we've seen these grids beforehand. It's basically a different representation of an array, and it's the same thing. We do the same thing over the entire array, and an array can be the screen. Ha-ha! So that's convenient. So how could that look like? So let's say we have conveniently as many pixels as we've got GPU cores. So each of these, so for instance, this core here is dealing with this pixel, this core here is dealing with this pixel, and so on and so forth. And now what we can say is, okay, look, you start with this little formula, and you know your coordinates. So this is like x and y is 0, and this is x and y is 3. And we give this function to each of them, and they're like, aha, all right. So my little number down here is 3. So I take 3 times 85, and 3 times 85, and 0, and that's the color that I'm going to put in. And each of them can run these in the same moment, because they don't have to know what the others have calculated. They don't care. They just go like, okay, this is my formula, off I go, right? And then they produce this in one go. The CPU can't do that. The CPU would have to do like, and so on and so forth, 16 times. And they just go like, yeah, we're done. What's next? Give me more stuff to do. And this thing down here, that's a JavaScript function. That's not complicated, I hope. Okay. You never know. Don't assume that people know stuff. So this is a JavaScript function, but that's also a shader. It's a function that takes input and produces an output in the expected format. So this is a simple shader. Now, okay, fair enough, we can't write shaders in JavaScript, but that's a shader. So let's revisit compositing real quick and disband this thing here. Anyway, so no. So compositing basically is just that, combining images by using a function. Okay, fair enough. And this function is happily called a shader. We just learned a new term for a function. It's a shader. Great. The shader has a specialty, which is it runs on these wonderful little cores in the GPU. And we can either write our own shaders, or conveniently, the browser has a bunch of shaders ready for us already. And these shaders can be seen in blend modes and filters. Now, let's have a look at that. So here we see the two images, the background and the young cat combined. And the only difference here is obviously how it looks. Okay, fair enough, but it looks differently because the shader function, the function that is used to combine these two color values from both of these images, is a different one. So this one is just taking the last value. So here basically it's like, okay, this is transparent, so I take the background, yada, yada, yada. This one's not transparent, so I just take this value and that's it. This one multiplies them, I think, and then so on and so forth we go, and then we have 16 different of them, and we don't have to write any shaders, we just say CSS blend mode screen, or overlay, or multiply, or add, or subtract, or whatever. So we have these built in, and that's pretty cool. So that means compositing can help us with a bunch of things. Compositing, first of all, can change where I copy things to. So that's a motion. I can move things around. In CSS and computer graphics, that's called a translation. We can rotate things, because as it turns out, rotation really is a shader that does a matrix multiplication with a rotation matrix that I'm not going to show you, but you find them in every beginner tutorial for computer graphics goes, and here's a matrix for rotation, and you go, what? And that's fine. We can also scale, because it's just multiplying a matrix with a value. That's also not too complicated. And then you can blend and filter. However, certain browsers don't have the shaders for that, so they have to actually repaint, which makes it slower. And that's how it is. And this is how a shader actually looks like. This one is written in the OpenGL shader language, or called GL slang. That's the short form of it, GLSL. And it looks a bit overwhelming, so let's go through it one by one. So first things first, we have a varying and a uniform. Ignore that, it's variables coming in, okay? That's just all we need to know at this point. Fuck that one as well. This is type information, so this one is an image, basically like a two-dimensional array, okay? And this one is an array with two items. So it's an x and y coordinate and an image, okay? And then what we do is we take the color of that image at the position. So we're having, you remember the x and y thing in our shader earlier on? That's pretty much the same thing. X and y is in coordinates, and then we take a color out of that image. So we basically hover over the image and go this color here. So depending on where the shader is, it's going to run with these values. Okay, and then we add the red, green, and blue values and divide by 3. What does that mean? Well, okay, here's not 255. Here is like from 0 to 1. Is like 1 is the 255 equivalent. So we have like red, green, and blue. Let's say it's blue, right? So blue in grayscale is like not very bright. So basically we have like 0 plus 1 divided by 3 is like 33%, like 0.33, and that means like it's a pretty dark kind of thing. It's a pretty dark value, and we use that as the red, green, and blue as the output. So we basically transform colors into grayscale values. And when you have a filter, you have a CSS filter that's called grayscale, and that's what it does. No magic. It's literally just taking the color, adding up the red, green, and blue, dividing by 3, and using that for red, green, and blue in the output. And that's how grayscale works. Now I want to rant a little bit, and that's because browsers. And it turns out that CSS filters and SVG filters are kind of the same, but not the same. So here we see a extract. This is a CSS blur filter applied to the circle, and I have enabled paint rect flashing in Chrome. Firefox has the same thing in the DevTools. It would flash a colorful area around it if there would be a paint. And the paint is something you don't want to see because it takes more time, because the CPU has to actually color in all the pixels. We can't use the shader there. So this is actually good news. The blur filter here on CSS elements is hardware accelerated because it just doesn't have to paint. It straight goes compositing in the shader. Nice. And I spoke to a few people, and they're like, yeah, and SVG filters are the same. I'm like, really? I mean, it makes sense, but really? No. See that? Bam. The rectangle of sadness, right? There's a lot of green here, which means all of the green pixels have been redrawn. One by one. Slower, not as nice. Unfortunately, they are not the same, and they should be the same, and there's browser bugs open to make it happen, but it is complicated. It is actually very complicated, and I'm just waiting for a magical hero to ride in to go, hey, we fixed SVG filters, and I'll be like, that is awesome, because I want these two to look the same, except for the color, obviously, but the green rectangle here should disappear, and it should not repaint. And if that ever happens, I'll bring them a beer. because holy crap, this is complicated, and I would love to see it land in browsers, because it would make our life easier, because we could use hardware-accelerated SVG filters. That's from a funny music video. Anyway, okay, blah, 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 shaders, compositing, whatever. Let's have a look at something real. So I would like to have this kind of thing. Okay, the app looks shit, but you know, this is about the interactions. So I have a button somewhere, and I swipe on my screen, and this drawer comes in, and I swipe again, and it disappears again. Not too hard to do. This is without Java. Well, it's one line of JavaScript that toggles the CSS class. Okay. That should be good, right? Let's have a look at the markup for this. So here's some HTML. It's semantic, Vadim. Look. nav, ul, li. That should read fine, right? Good. And then we have some CSS that does this. Can you spot the problem? Is there a problem? Yeah? Yes? No? Maybe? Who thinks there's a problem? Shh. Okay, good. Moving swiftly on. So basically what we're doing is we're moving it 200, like minus 200 pixels, so which means we are moving it left out of the screen. And then we say transition. So if the left property changes, we take 1.2 seconds and some ease to actually do this, like this, right? This kind of animation comes from this wonderful transition property down here. Okay, so the things that we are interested in is the left property and the transition property. And when I click on it or swipe it or whatever, then I add a class that just does this. It just changes the left to 0, which means it's now moving towards, basically it's jumping to the screen, but actually because there's transition, it kind of nicely transitions. And in the timeline, it looks like this. It's pretty green. That's good, right? No? That here is the frames, and it should be like somewhere here, and it's constantly not at 60 frames per second. So that's not very good. And like, green or not, there's a lot of work going on here, right? That's a lot of work. Why is there so much work going on? Well, can we do better? First things first, that's how it looks when you enable paint rect flashing. So each time it changes color, that means it has been repainted. All the pixels have been repainted. So that looks, this area right here, that's where the party's going on, right? That's some serious repaint disco going on there. And I like disco and stuff and dancing. Actually, I hate dancing, but it doesn't matter. You know, dancing and disco is nice and was probably a thing in the 70s and 80s, but we're in a different time. So can we do better? Yes, we can. Because what happens here is the green thing that we saw on the timeline is actually painting. So what we do is we have some JavaScript that changes the style because it applies this additional class. And you know, okay, we don't do layout really because, you know, screw it, because we don't have to like move things around, so we don't do layout, good. But we're still painting all the pixels again, and then we composite things again. And the composite doesn't really do much here, it's all the painting. And painting is a painful process because we have to do all the little happy accidents, as Bob Ross would say. So can we do better? Yes, yes we can. Have a look at that. Do you see a difference? Let me help you. We're still doing a transform, but this time we do translate 3D minus 200 pixels. So it's the same thing. It moves it over using a 3D translation, sorry. And we now transition on transform, and it's pretty much the same thing. So basically, when we click, the class now does no longer change left. It changes the translate to 0. Okay, good, sweet. Ah, that looks better. Actually, I think it should not paint at all. Chrome does not paint in this case. I'm probably asking a few people at Mozilla if that's a browser bug or if it's me doing something really stupid. But at least no longer disco, right? And look at that. Wow, that's better. There's a whole lot of nothing here. And I like that. I like that there's nothing going on. Also, the frames are just like, wow, whatever, have a party. That's the old version. You can see, I think we have improved, especially here in terms of frames, right? We had these frame drops, no longer. We don't do all the work here, no longer. It's all good. We are all having a good time together. Nice. So what have we done? Well, we have avoided paint. We are now no longer painting, we are now just compositing. And that's because instead of changing a position, we have done a translation. And the translation is something that, compositing can do really well. So we are basically skipping and just using a shader that does the moving around bit. And that's fast because it does it in parallel and it's really nice and funny. Cool. So that's what we want to be at. And we want to do that because performance, as Paul Lewis once famously said, is the art of avoiding work, which you probably should not say when you're doing a job interview. But generally speaking, if you say it when I'm interviewing you for a job, that's a good thing to say, because I do believe that if we are not working on stupid stuff and work on good things, that's an improvement. So here we are not working at like repainting pixels that have been painted before just because they're on a different position. Our renderer and our main thread can do other things and better things and nicer things for us. For instance, add confetti or unicorns. Okay, now comes the interesting part. Everybody strap in. We are doing a quiz. I'm running over time, but at this point, I don't care. You have to sit through this. There's an after party later on. I tell you about it. So here we have an element that is translated x0, so it's wherever it has been before. And then after 2 seconds, we are changing its x position to 200 pixels to the right. And the question is, will it paint? Good. It was okay, good. Pop culture is tricky. I'm not always sure if that works. Have a look. Do you see that? No, it paints. But why? Why, Martin? Why do you lie to us? You said moving things around with the translation. It's hardware accelerated, and now it isn't. Well, the reason behind it is that I don't tell you the full truth just yet, but I'm gonna. So remember, compositing is about images, or in the browser lingo, layers being combined. Now, layers have a little bit of a downside as well, which is, they have to store them somewhere, so we need more memory for it. And if we have a page like Facebook or Yandex or Contactio or something, or Habr, I don't know, they have a lot of items. So making each of them into a layer and then never moving them is not good, because we're gonna have to use a lot of memory that we could spend elsewhere. Also, if we have a longer list of layers that we have to composite, more work has to go into them, and if there's no moving around, then why, right? So instead, the browser goes, I'm going to be clever about this. And for instance, if it's a canvas or video element, they are changing a lot. So yeah, I have to repaint them anyways. Let's use a layer for that one so that I can kind of like do it asynchronously. Nice. 3D transforms, because someone said, oh, 2D transforms are usually not animated. And let's just do it like that. 3D transforms, very different thing, very tricky thing, because the z-axis we have to do like perspective transformation and stuff. Let's put that onto a layer, because then the shader can really kick in and do nice things. The same goes if it's an animation. So if someone goes, I have a translation of whatever sort, even if it's a 2D translation, but I do it often in an animation, then the browser goes, got you, buddy. I'll move that into a layer, and then we can composite it using the shader. And then there's the will change property, which does not necessarily create a layer and does not necessarily cause compositing, but the browser at least tries to understand if there is a need and if there is a performance win, if that would be composited. So it's not necessarily changing things, but it signals to the browser, hey, I'm doing things now. And by the way, the 3D transformations, that's the reason why the translate Z0 hack works. Because it goes, translate Z, that's a 3D transformation. So let's composite this. Okay, let's play this again. Slightly different code. 2 seconds later, we change it. What do you think? Oh, yes, maybe. Да, нет, наверное. Okay. Bam! It does not, because it's a 3D transformation. Okay, fair enough. That was a tricky one. Now, what's about this one? If you look at this one, we have an animation, and we do something. No? Very well. Thank you very much. That is the right answer because it's a keyframe animation and it's a translate only, like it doesn't do any weird shit. That means that we are hardware accelerated. Nice. Okay. I'll run through this real quick. Now, there's people who try to basically re-implement things in WebGL because WebGL is really fast. And then there's other people who go like, no, I do Canvas 2D because I'm only doing 2D graphics. And both people actually have problems. And let's have a look at what kind of problems these are. So I pose a challenge. I give you an image, and I want you to resize it and draw it to a random position on a canvas as often as you can, and tell me how fast you're going to go. Okay. Right, that's a good challenge. So this is what I would probably write if I have a Canvas 2D. So all the setup code out of the way, I would say, okay, we have a bunch of images, maybe 100, maybe 500, maybe 1,000, and I pick a random position, and I pick a random size, and then I draw it at the random position and with the size scaled as I want it. I'm going to show you what that looks like in WebGL. It's a little more code, maybe a few lines more. So if you can't read that, that is fine. Okay, this is just to illustrate a point. So this is the code. And there's a few, like, this is one part of the code. There's another part of the code which is like a few parts of the setup, just the very minimal setup, which is this. And it does the same thing. So I would say, yeah, we have a winner in this round. Okay, but let's look at the frames per second. So here you see the frames per second on the y-axis and the amount of images, amount of repetitions that we do on the x-axis. So for one element, we are safe. We are rocking it, right? So one image, I can do that. I'm really good at this in Canvas 2D. I get 60 frames per second. Let's not talk about the others because we kind of want to be here. And I think the minimum is like here. It's like 12, 15 frames per second. So basically at 500 images being drawn, we are a slideshow. Okay. So, but I'm pretty sure, we've written so much code, WebGL is not going to get any better. Okay, fair enough. But you can experiment with hardware-accelerated canvases. So the Canvas 2D can be switched into a mode where it tries to do things in shaders as good as it can. But the JavaScript API does not really make it easy to do that. But we're still getting something out of it. So now we're starting at 10,000 elements. And the Canvas does a proper 7 frames per second. That's a very fast slideshow, I would say. Very good. Very well done. At 25,000, even WebGL goes, ooh, there's more efficient ways of doing that. To be fair, that's not WebGL. I've written a really bad shader because I couldn't be arsed to actually write a proper shader. So if your shader is not very good, 25,000 is where it starts to not look very nice anymore. But I think we kind of have a draw here. And let's kind of recapitulate. So Canvas, while being easier to write, but then again, there's WebGL libraries that take away the pain of writing the code. They don't have access to the shader pipeline, so they can't run things in parallel, so they're not as fast, unfortunately. And WebGL goes like, hey, GPUs, are you my friends? And the GPUs go, woo! And it's like, to the window, to the wall, and they're having a good time. So it's a party of graphics rendering, which is really cool. Which gives us more performance, but it also depends on the hardware. If you have a really, really old computer with Internet Explorer 9, you might not. Internet Explorer 11 is fine, by the way. But if you have not a relatively modern browser, then WebGL does not look very good. And modern browsers still, IE 11, I mean, come on. I mean, I've seen banks that go, we run on IE 11 because of security. And I'm like, no. Anyway, so should we just do WebGL for everything? And it has been tried. Because it's faster, right? It has all these awesome things, and we don't have to do all the slow things, and oh my God. No. Because it depends on what you're trying to do. If you're trying to write a game, And sure, go for it and ignore all the other things. But if you're making a website or anything that is to be used by anyone that is not necessarily fine with waiting 10 seconds for something to download, then you should probably go for regular HTML and CSS, because that gives you semantic UI elements. We've seen in the talk before me that semantics are not very hard if you write proper HTML and maybe spice it up a little bit with area elements and stuff. And also, you have the UI primitives. We have seen a button already does, like, I can use the spacebar, I can use enter, I can use click, I can probably, I don't know, stare at it long enough or something, I don't know. But you get all these primitives. You have to re-implement all of that. You don't have events in WebGL. It doesn't know. If you click, it goes like, what? So, you have to do all of that work, all figuring out where's the mouse pointer, where's it pointing, what's behind the mouse pointer, all that kind of stuff you have to do yourself in WebGL. For images, for graphics, you can actually use SVG for a lot of things, especially 3D and effects and stuff can also be done in SVG. And some things are actually already hardware accelerated, and some other things hopefully at some point will be when I have to pay someone a beer. And it's really cool because it's responsive to the size. WebGL does not know about window size. It goes, no, I don't, what? And the canvas can also be used if you do like simple things. For instance, just pipe through a video or something like that, or just draw an image and change something in the image, or have someone like paint or something like that. Then canvas is really good. But for 3D graphics and also 2D graphics that can use the shader axis, that's where WebGL comes in. And that's why a lot of the libraries that do 2D games on the web, for instance, Phaser, they are using WebGL because they then can do like a lot of effects and blending and effects and stuff and all that kind of stuff in WebGL. That's why it's kind of used for these purposes. So pick the right tool for what you're trying to do. And that was all I wanted to say. The slides are already online. I'm around for the day. I'm taking hilarious selfies, which I'm going to do now if I find, here's the camera. So this is the 300, I'm working with